Right.
Okay, well, thank you so much, and it's always a pleasure to be here in Singapore and be in the Stein crowd. Also to hear about the interesting new developments in the Stein world. So the take-home story that I'd like to convey from this talk is just that the use of what I'm calling Stein discrepancies, and now I have to give you some caution, these aren't exactly the same as the Stein discrepancies that Xiong talked about yesterday, but they're kind of in spirit the same, which is there are measures which are constructed specifically to see how far you are away, in this case from the Gaussian, the way that Xiong did yesterday, measures that were constructed to see how far you're away from some target, right? This is going to be based on work that was done by Lapowski, Plan, and Verschinen on the single index models, which I will explain. Single index model. So that was part of the title. Some of the other words that you might have heard in the title were non-Gaussian sensing, and Stein type discrepancies. Okay.
If you want a better view, you can come to the front.
I'm sorry? Oh,
I mean,
yeah, so please
yeah,
feel free
if you want a better view, you can come to the front.
Yeah. I'll try to write a little bigger, and, but maybe it would help if you, so don't have to be shy. What's that, bigger? Okay, I'll try to write bigger, but maybe also it help. Okay, so with the graduate students, this is joint work with Xiaohan Wei. Although he was a graduate student at USC, he wasn't my graduate student, and he didn't work on his thesis with me. This is just kind of a one-off that he did on the side from the engineering department, and he's accepted a job at Facebook. So hope he'll still be in the technical area. So very well. So let's talk about a single index model, but I'm going to warm you up by talking about something which is very close to the hearts of statisticians, which is, let's start with a simple regression model. And if you don't like the notation I use for regression model, then you should blame these authors. Okay. So, because it's going to be different from what we're used to. So suppose I have an observation yi, which is a vector. So if I have the dot product of a vector ai, that's going to be my sensing vector, epsilon I. X is my unknown, so X would be the y equals x beta plus epsilon version of regression. This X is the beta, okay? All right, and then X is going to be an element of some set K and RD. This may be some kind of a structured set. I mean, you may think of X as some set of sparse vectors, but that's not going to enter really into the talk because I'm going to focus on the Stein portion of the talk. Okay. All right. So let's. So now we know that X doesn't depend on I. That's kind of a that's what's fixed, and we're going to try to recover or estimate X. Then let me make a couple of generalizations, and I'm also going to drop the indices here. So we have that the expectation of y given A is equal to the dot product AX. Now the sensing vector A, throughout the talk, it's just going to be, well, it has to be decomponents, right? So I'm going to make these IID, they're always going to be mean 0, they're always going to be variance 1, okay? And in the special case, they will be Gaussian, okay? So now this is a slight generalization, right, of your standard linear model, right? We're going to take M replications. But to get the single index model, I'm not going to let you observe this dot product. There's going to be an unknown function h, and you're only going to be able to observe h of that dot product. Okay. So that's what you need to do. Okay, so that seems like maybe it's not even possible, right? So one sort of common example would be where h of u is just the sine function, sine of u, okay? So you get to see whether that dot product is positive or negative. That's all you get to observe, right? And you're asked to reconstruct the x. So one thing you can see right away from, this is called one-bit compressed sensing. Maybe you've heard that. That's one-bit compressed sensing. So one thing you can see from this, this particular example is that in general, you're not going to be able to recover x, the length of x. Right? You may be able to recover x up to its length, right? But if I change x by a constant, then I could absorb that constant into this unknown function. Okay? So we can therefore assume, without loss of generality, that x should be non-zero for this to make sense, right? So therefore I can standardize it by its non-zero length. So we can assume with that loss of generality that x has length 1. So for this one-bit compressed sensing model, let's think of what would happen even in, say, a noiseless case where you're observing the sign of the dot product, right? You would think that you would get, this would be, this is the sensing vector, so you test the dot product with a, say, Gaussian vector A, right? And then you get some positives, right? You should get some negatives. And then what you hope happens, right, is that the positives and the negatives are separated by a hyperplane. Right? And therefore, you would know your x, right, because it has to be the normal to this hyperplane. Right? So your x could be recovered, at least up to length, right, by knowing what the normal to that hyperplane is, if you get this kind of a positive and negative pattern that's separated. Okay? Now, if that story makes sense to you, then your intuition is very Gaussian. Because if your sensing vector is not Gaussian, here's a simple example which shows that your x can be, in fact, unrecoverable, right? So let's take the case where we have an x, say 2 dimensions. So I'll look at x to be, this is my unknown, right? And let's take a, so the components, all right, little a for the components. So let's take a to be Rademacher variables, which are going to be +1, -1 with equal probability, okay? So that's definitely non-Gaussian. Let's see, maybe it runs us into some trouble. It does, because if we have this as x, or if we have this as x, I can't tell the difference when I take dot products with those symmetric Bernoulli variables, because the sign is determined only by the first component. Okay? So in this case, the fact that we'll see, I'll prove to you in a minute that it's actually things will work if we have Gaussian, but this shows that there's going to be some perhaps unrecoverable error that you have to incur for the non-Gaussian case, even if the sample size gets large, right? So this is an error in here which has nothing to do with your sample size, right? It has to do with sort of the nature of that. Okay, so the first question that maybe you should ask is, if I think this works, then how am I going to estimate this unknown, right? So the way I'll estimate this unknown, well, so I think back to my regression model. I don't know h, right? I also may not know the distribution of A either, right? So maybe I'm not given the distribution of A. So, well, one simple-minded thing, and we started with this nice simple regression, and one simple-minded way we could do estimation is just by least squares. I mean, that couldn't possibly work, could it? But let's see, right? So let's look at least squares. So least squares would say we take the sum yi minus a, and then I've got a variable t, right, a vector. So I'm going to look for the t. It's going to minimize this quantity, this least squares quantity, right? Okay, so I want to minimize that. And since I've assumed that x as norm 1, I may as well for now assume, maybe I'll change this in a little bit, but I'll tell you why if I do. So we should assume that t also has length 1. Okay, so what happens here, all right? So let me expand this out, right? So this is going to be 1 over m, sum I goes from 1 to m, yi squared minus twice yi a t plus square at squared, okay? So I can't do anything, right, with, so I want to find the t on the unit sphere in d dimensions that minimizes this, right? That's the least squares estimator, right? Okay. So I can't, the t doesn't affect this, okay? Sorry, so if you have a question? Yeah, they do. Thank you. Please. So, thank you. So please help anytime you see the opportunity. Okay. Good. So can't do anything about the y's, right? Also, if I had a large sample, this is just going to be like its expectation, which I know is the length of t squared. Right? So I might as well replace this by the expectation that I would get in a large sample. which means the only thing left of action is this. Right? So we can make another function instead of minimizing, then we want to maximize, right, because it's got minus, so why don't we maximize yi, ai, t. So let's maximize this one instead of minimizing that one. Okay? Okay, so now there's going to be two components in the error that we're going to make, right? And one is the component, error component that we make because this isn't at its limit yet. Okay? So if we maximize this, then we're not going to get what we would get if we had more infinite samples, right? So there's going to be some kind of a error. Let's write SD minus 1 for the sphere, right, in d dimensions, right? Okay, so that's going to be one source of error, and I won't talk too much about it, but I'll write down the bound. Another source of error is, well, what if we had a large sample, an infinite sample, and we maximized this? Okay, then what would happen, right? Okay, and we know in some cases that we won't recover, right? Even if we have an infinite sample, right? So the expected value of Fm is just an expected value, and here I'm going to drop the subscript. Okay, so expected value of y a comma t, right? So this is expected value of y a t. Okay, but so now let's get back to the model, right? The model says that the conditional expectation of y given a is this h, right? So I condition and uncondition, and I can replace the y by expected value of at, and then h of the inner product of a and the true value x. Okay. All right, so let's see what we're going to do with that. Now, what I'd like to do is notice that t and x in this d-dimensional space span a two-dimensional subspace. Okay, so let's make a orthogonal basis of that subspace into x and an x perp. Okay, so I have two orthogonal vectors which span the space of x and t. And I'm going to do a decomposition, right, of t. So I can write t, right, because I sort of want to know how much x there is in t. So I write t as inner product tx, x, and these are all, unit vectors, okay, because we're on the sphere now. And then I have t x perp, x perp. Okay, so I'm just doing a decomposition of my t into the x direction and into the orthogonal direction in the space spanned by x and t. Okay, so that means that we can write this, right? So let's take that inner product here. So this is equal to so a t here. I get a coefficient tx from this term, and then a x, and then I multiply by h of ax. Okay. And then when I take this part of the t, right, then I get t x perp as the coefficient. Then I get a against x perp, and then I get h against ax. Okay. Okay, so simple so far, right? I mean, there's nothing here, nothing much going on here, right? Okay. So Stein is about to appear here. Okay? Somewhere, if you look at this, there is Stein. Okay? So all I will do is a change it. So suppose now that you have Gaussian sensing vectors. Okay? For the moment. Suppose that these A's are Gaussian. Then let's call y equal ax. Okay, that would be what? Normal 0, 1, right? This term here would be y, h of y. So there's something here, Steiny. Okay? All right? So continuing with Gaussian, right? So here we have tx. So let me make the notation here. So I'm going to write y to be inner product A with x, and y perp to the inner product A and x perp. Okay. Also, I'm going to make lambda. So there's going to be one non-degeneracy condition that I'd like to make is that this ax h of ax is not 0. So let's have this to be non-zero. And in fact, let's for now, really without loss of generality, just take that to be positive. Okay, so in the Gaussian case, what's going to happen to this term, right? So I can write this then, I'll go back here. So this is going to be tx, and then this is just going to be my lambda, right? This is my expectation y, h of y, and I'm calling that lambda, and I'm assuming that that's going to be positive, okay? Good? Yeah. Okay. Now what about this, right? So this term here, right, I have plus t x perp. And this is going to be expectation, right? So I get expectation of y perp, right? That's y perp on h of y. Okay. And what do we know about the relation between y perp and y? Well, first of all, we know that y and y perp are jointly Gaussian, right? In fact, they're projections of the same Gaussian vector on orthogonal directions. Hence, they're independent. Right? So in the Gaussian case, this is what makes the Gaussian case nice, which is why we want to see what happens when we're close to the Gaussian case, right? So for the Gaussian case, this is 0, right, when A is Gaussian. Okay, so in the Gaussian case, right, we're getting, what did we say at infinity, right? This is going to be the expectation of m goes to infinity. We want to maximize this expectation FMT, right? So this is the quantity that we're maximizing, right? So we're maximizing only this, right, in the Gaussian case. Right? So we want to maximize, this part goes away, right? So I only write this as expectation of y perp h of y. Okay, so in the Gaussian case, we want to maximize t x lambda for t over the unit sphere in d dimensions. Well, this is the same as, I can bring the lambda, that's a positive constant, right? So this can come outside, right? And so how do we maximize the inner product of t and x over the unit sphere when x is unit sphere? We just set t equal to x. Right? So maxed at t equal to x. It's kind of surprising, right? So in the Gaussian case, it says we can, right, if we have, m tending to infinity, we actually completely recover, right? So and to me, it was a surprising result that you can do that, right? Because all you're allowed is, this unknown, so you don't even know what your h is, right? So you've observed, right, just some unknown function of this inner product. And yet, if you have Gaussian sensing, then this doesn't prevent you from recovering your vector x up to length. Okay, so now let's talk about what happens in the non-Gaussian case, right? And so what's the price? What's the price that you pay if you're not Gaussian, right? So you can see that what's making this work is that the expectation of y at, right, minus this, say, lambda tx, this is 0, right? In the Gaussian case, right? So we want to see how non-zero that is in the non-Gaussian case, right? So let's look at, in the non-Gaussian case, let's define a measure of, badness. And the measure of badness would be what's the worst this can be, okay? So let's look at t of like 1, and let's take the soup over all those. Okay, so that's your worst case. And in the Gaussian, right, no matter what the t is, that expectation inside does match this lambda tx. Okay, so this is the price alpha. Okay, so let's call that alpha. And now I have alpha, I can tell you what the result is, and I can tell you how it compares to what the previous authors did in this case. There's sort of two improvements, and I'll focus on the one that has to do with Stein. Okay? So the result in this paper with Chauhan says the following. There's some complexity to it, which I'll just shove under the rug, I think. But here, so again, a couple of details. So let's call xm hat. So xm hat to be the arg, say, min of this function fmt. And also, so in these types of optimizations, some people don't like to have non-convex optimization. So instead of letting t, we said that x is of unit length, and therefore we're going to have t of unit length, but then we have to optimize over a non-convex region. Okay, so what you can do instead is you can make your k here convex, and you want this lambda multiple to be in k. So that would be the, so instead of, so if you don't want to do non-convex optimization, then you pay that price, and you find a k for it. And if you know the direction, if you have an idea of what the direction is, then you could just extend it or shrink it so that you're pretty sure you've captured that multiple. Okay? And then you can make a convex optimization. And under that condition, you know, the result that says that xm hat minus the true x is bigger than alpha plus, so here we have, so we're going to assume, I'm going to just write this down, but I'm going to focus on the alpha when I'm done. So we're going to assume that A is a sub-Gaussian, okay? And we're going to assume that Y is sub-Gaussian. So these are the sub-Gaussian norms. And then there's going to be Gaussian width of a certain set. Right in a minute, it won't be important. So this is less than e to the minus e. Okay, so this is the result that we get when I do this optimization, that we're off, you know, from the true by a factor that depends on those two errors, right? So this is the error that I talked about here. So this part comes from this term, right? Taking the soup, and that is achieved by Talleyrand generic chaining argument. And if this were a Talleyrand conference, then I would tell you all about that, and I'm glad it's not, so that I get to tell you about the alpha. Okay, so I'm just going to skip it, because it is a little messy. Okay, and this inside here is the Gaussian width of the descent cone of k at lambda x. Okay, so it's just what goes in there. It's just some kind of measure of how large that cone is at the point lambda x, which you hope to capture by making your set k big enough. Okay, but that's all I'm going to say about it, except for how we improved the previous results. So the previous result of the authors that I just erased, so for this Lapanowski, Plan-Verschinnen paper, they had some assumptions, and one of the assumptions, a few assumptions, and one was that the yi's could just be binary. Okay. And they had the h function match R into some bounded region. Okay, so they had this, all right, and so we, dropped these assumptions. Okay, so we have just that y is sub-Gaussian and h could be general. Okay, and so we got the sub-exponential bound because you have the a and the y appearing together, right? So if this is sub-Gaussian, this is sub-Gaussian. I have sub-exponential. Right, so we have a sub-exponential bound, whereas the earlier authors got a sub-Gaussian bound, right, under the stronger conditions. Okay, but I really just want to talk about. There's a 2 alpha because it's a cross term, right? So there's a 2 that appears here, which propagates. Okay, so that's the result that I really want to focus on this alpha, and the story is going to be, as I said, how simple this alpha is to bound. In terms of these Stein-like quantities. Okay, that's my goal. Okay, so what can I erase? Maybe this. Okay, so if we're talking non-Gaussian, right? Let's start with, again, the Gaussian, right? So suppose I have, our famous, so all the A's are mean zero variance 1. Here's the well-known Stein identity, and now we don't have that. We can't use that because I'm saying that A is no longer Gaussian, right? So now what are we going to do? You have to somehow change this identity so that it adapts to a non-Gaussian case, right? So let me give you, I'm sure there's an infinite number of ways, but let me give you 3 ways and mainly talk about 2 of them. So there's the Stein kernel. Stein kernel. So Stein kernel is a T. So we all see that on the right-hand side, right before f prime of A, you see it's multiplied by 1. Right? You all see the 1 there, right? So let's replace. So that's only true in the Gaussian case, and in the non-Gaussian case, maybe, right? It's not always true that you can find such a Stein kernel, but so let's have T of A. Right, I'm going to take T of A to be a function of A, if necessary, by conditioning on A. Right, so there's a Stein kernel, and it appeared, I guess, by Kakoulis and Papanasthiou in 92 was the first I could trace this back to. Okay? All right. Then we have the zero bias, right? So we can change the right-hand side in another way. F of A. Excitation F prime A star. So this was myself and Gesine Reinert, 97, and this always exists. So for any mean zero variance 1 random variable, you can always find such an A star. Okay. And then there's a score function. I don't know who to attribute it to. The score function has been known in statistics for ages, right? So I'm not sure if someone tell me it's been where it came in the Stein world. So these are changing the right-hand side, and the score function changes the left-hand side. So score function is some function of A, f of A, is equal to an expectation of f prime A. Okay, so the idea that I'm telling you about was actually used in other works by some of those who are present. So in GLM, so the zero bias was used by Bayadi, Dicker, and Murat in GLM, and score function was used by Krishna Subramanian, Yu, and Yang for cases which included single index models. It's a nice result. Here, I'm being more ignorant than they are. I'm being more ignorant in that I don't know my distribution. Right? I don't know the distribution of A, so I can't use S of A. Right? So score function, right, which is the derivative of the log of the density, you need to know the density. Okay, so that's some history. I'm going to focus then on the first 2, because I can't use the third one here if I don't know the density. And let's see what kind of nice Stein quantities turn up. Right. So yeah. So I guess I was thinking of, so these. You're right. I guess we could look at this. And I'm playing what-if games. I could play what-if games here. Yeah. Again, right. Yeah. I guess I do get. So for some of the things, I will be able to get sort of universal bounds that depend on that depend on low-order moments and things like that. So that I'll be able to do. I don't think I can do that in all cases. But yeah, we could look at Stein functions. It's score functions. But yeah, but here, I guess yeah, that's true. So if you know the score function, then you have to adjust for you don't do the direct least squares. You throw something into the least squares if you know the score function. So I have to think about how am I going to do the least squares if I know or not know the density. Okay, so this is my alpha, and as you see inside here, right, it's also going to be, if we get back to this argument where I have this EYAT minus inner product TX lambda, that equals what's the bad part, right, that causes the trouble is this, right? That's what's causing the trouble, which is 0 in the Gaussian case, right? Cauchy-Schwarz, if these vectors are unit length, then I can do Cauchy-Schwarz and this goes away, right? So I can bound this by my alpha. So right away it's kind of a nicer form, I'm thinking Steinwise. So y perp hy. Okay. So the previous authors used things like total variation distance and other kinds of measures, which are fine, but they're not sort of adapted in a certain way to this particular problem, whereas the Stein, these kind of Stein ideas are. Okay, so we can see what appears. Okay, so let's look at expectation from these two, 1 and 2, expectation h of y, like that. Okay, so y perp, which I wrote there, is the inner product of A and this x perp vector. So this is expectation sum, I goes from 1 to n, so it's going to be AI xi perp, and then h, and I can AI xi, and then everything else is going to be independent. Right, so that's y perp h of y. Okay. So if we look at, and I'm putting this aside right here because this part is independent, right? So I'm going to condition, we'll condition on this and then using the fact that these are all independent, right? So I can apply this coordinate-wise, basically. Okay. So when I condition on this independent part, then I'll apply the identity here. Okay. So for example, for Stein kernels, right, what are we going to get? Right. So the Stein kernel says that we have the expectation. What happens in the Stein kernel? Well, the A goes away, and then I replace it with a TA, and I have to take the derivative. Right. So the A goes away. There's a TA, so x perp, and then a TAI, and I take the derivative, and I get an xi here from taking the derivative, because the derivative with respect to that AI, and then I have, it's the same y, right? So it's just, so the right-hand side doesn't, this A is the same as this A, right? Unlike what's going to happen for zero bias, so I have h prime of y. Okay, so that's what happens with the Stein kernel, right? So we're not quite done, right? Because it's going to simplify a little bit. So everyone see where how this occurred, right? So this xi is this xi, and I take the derivative, so I get h prime, derivative with respect to this ai, so an xi comes out, and then this one. Okay. All right, so actually there's a nicer way to form for this, and what I should notice here is, one thing to notice, is the expectation of TA is 1, because that's the variance, right? So if I look at f of A to be A, this is the second moment, which is 1, so the expected value of the Stein kernel is 1, right? So maybe I should compare the Stein kernel to 1, because I want these measures to recover the fact that for Gaussian sensing, this alpha is 0, okay? So, well, here's how you do that. You can write this as expectation sum I goes from 1 to m, xi perp xi. Well, let's see in a moment. I could just put this TA minus 1, TAI minus 1 here, because h prime isn't really in the sum, right? So h prime is pulled out of the sum. When I put a 1 in here, I have xi perp and xi, and there's a orthogonal. So I didn't add anything. Okay, and now, right, let's just take absolute value, use Cauchy-Schwarz, right? So this is going to be less than or equal to, so we've got h prime of y, right? A couple more steps. I goes from 1 to m, xi perp xi, and then expectation out in front still, and then TAI minus 1. Okay? everything's ID, right? So when I take expectation, these are all the same, right? So this is going to be less than H perp, right? And then expectation of TA, the generic A minus 1. And these vectors, again, are unit vectors, so I Cauchy-Schwarz, and it's bounded by 1. And I'm done. Okay, so this is my alpha, right? Yes? Linear case, right? Yeah. Yeah. So just one moment. So yeah, so that's going to happen. That's just about to happen here. Okay, so we don't get that for the Stein kernel, but we're going to get that. We'll see that we recover the linear case. So here I have a bound which doesn't recover the fact that Shang noticed, which is that, of course, if it's linear, right, then we're back to linear regression, and somehow that should still work, right? Linear regression should still work even though we generalized H and then made it specific again. Okay, so another case would be for this zero bias, right? And there what happens, right? So then we get this expectation of some I goes from 1 to M AI. Oops, so the AI is now we're going to take the expectation over that AI, right, and use the Stein identity. So if we do that, right, again, this AI vanishes, right? I get xi perp, okay? And I take the derivative, right? So again, I get this xi, right? Same as before, but now what's different is I get h prime, and I replace AI by the zero bias, xi plus y minus AI xi. Okay. Now what happens, right? So this doesn't look like maybe it's going to be such a nice form, right? But I claim, as you'll see, right? Actually, you'll see right away. Go here. So this is equal to. So I'll do kind of the same thing that I did here, which is I'll add something. I'll add 0 to it somehow. I'll subtract 0 from it, and I get sum. I goes from 1 to m xi perp xi, so let's write this again. So it's h prime ai star xi plus y minus ai xi, and let's just subtract h prime ai xi. This is just y, right? So just inside this h prime is just y. So this doesn't depend on I, right? So it's not really in the sum, right? Which means I'm just getting xi perp xi, and those are orthogonal. Right? So that's legal, right? Okay. And now let's take absolute value, right, and kind of do the same that we did with previous, right? And so this is going to be less than or equal to, right? So I get second derivative. So h double prime. Like that. You're happy now. I'm happy too. Okay. So we get h double prime. It says that you recover 0 when the function is linear, and then you get sum I goes from 1 to m xi perp xi, and then mean value theorem says that you have h double prime, right, times the difference of these, but they only differ here, right? First term. So I get another xi, right? And then I get ai squared, ai star minus ai. Okay, and that works for any way. That works for any way in which I can couple ai and ai star. In particular, it works for the optimal coupling, which gives me the Wasserstein one distance between a and a star, right? And my ID, right, they're all the same. So this is going to be less than or equal to if I use Cauchy-Schwarz there, which I want to do. So less than or equal to this times gamma A, where gamma A is the Wasserstein one distance between A and A star. Okay. It's kind of interesting. Usually this Wasserstein one distance appears like as a bound to get something else, right? It appears as an upper bound. So we know that the Wasserstein distance between A and a normal is less than twice the Wasserstein distance between A and A star. So this, it sort of uses it as a device, mostly in Stein's method, to get this, but here it comes as itself without it trying to serve another purpose, right? So, one thing, again, we can see from this inequality, right, that when you're linear it's 0, and also it recovers the Gaussian case, right? When you're Gaussian, this is 0, and therefore alpha is 0, as we showed again. I showed earlier. So I don't have time, but let me write the bounds for 1-bit compressed sensing, which of course isn't differentiable, so 1-bit compressed sensing doesn't fall under those rubrics, right? But the previous bound that we improved, so the previous authors had a bound of a cubed times the infinity norm to the 1/2. This was I Laplanovsky plan for Shinin, and then we improved this to explicit constant 10 a cubed x infinity gamma a. So their bound, as you see, it didn't recover the Gaussian, it didn't say at the Gaussian case the cost was 0. We managed to insert the gamma a. This is for the 1-bit compressed sensing. Right? Okay, so I guess I have 5 minutes. Let me just say 2 words about, this plays nicely also with sort of adversarial noise corruption, or just noise corruption in general, right? So you could have your noise corrupted, say by mixing, which is like every once in a while your adversary can insert a bad sensing vector, right? So mix your nice Gaussian distribution with another distribution, or your adversary can add noise, right? So that'd be additive kind of corruption, and these. Just write one thing. So maybe you're trying to use Gaussian because it's nice, but things get corrupted, and they could get corrupted by, it's a Gaussian as long as the corrupting event didn't occur, and maybe there's a probability epsilon event which is independent of the G and the A, right? This would be sort of a mixing type of corruption, or maybe you have an additive type of corruption where your adversary can add in some noise that you don't want, right? And these are very nicely handled by these, for example, for these Stein ideas. For example, here, if you have total variation distance, then this one might be sort of easy to get a bounds between this mixed version between G and A, and the total variation distances between G and A, right? But maybe not so easy to have total variation here, right? To get total variation distance between G, maybe or maybe not, but it works out nicely in the case for the Stein kernels and also zero bias, and for the kernels, I'll just write down the answer. The kernels, you have alpha is less than h prime expected value t minus 1, and then there's just an epsilon in front. So it just scales linearly. So alpha is less than this. And then for zero bias, this is a very simple computation, but I won't do it. So you get epsilon to the 3/2 h double prime gamma a. So it's got some nice properties that make it easy to manipulate for other statistical purposes. Okay, I think I'm up out of time, so thanks. No, so H just works, so when H is not differentiable, then you end up, well, so I don't know in general H is not differentiable, but I only know the case for the sine function, right? In the sine function, you end up dealing with things like the absolute value of, so if you look at like AX, H of AX, right, this is exactly equal to the absolute value of AX. So you just handle these kinds of things directly, and taking expected values of the H, which are the sign, just gives you things that involve the probability that it's positive and the probability that it's negative, and you can use Barrier-Seen on that. So the sine function really might not, the sine function might not be a good example of what happens in non-differentiability because it's very special, right? So I didn't try other non-differentiable functions, but for this one, very nice things happen where you don't have to do any smoothing.
Yes.
Okay. Ah, I see. Yeah, it's also you can recover. Okay, so that's a nice observation. Thank you.
Are there any more questions? Well, if not, let's thank Larry again.
Thank you.